So a little bit of background about Euclid and the Pythagorean Theorem. So we mentioned Hippocrates last time. Euclid came after Hippocrates by about 100 years. And Hippocrates, remember, wrote an early version of the Elements, which was basically a systematic organization of geometric ideas. Remember, the Greeks had a particular obsession with the intellectual realm. Okay? They sort of saw the intellectual realm as, there was some kind of spiritual connection there. The physical, on the other hand, was something that they saw serious problems with. They actually saw other cultures as being fundamentally flawed, as having focused too much on the physical and being anchored too much in the physical to the point where they were only interested in applications and whatnot. The Greeks saw that as a giant mistake. And as I mentioned before, that caused them to have this kind of incorrect notion at some point of the physical being bad and the spiritual or intellectual realm being good. Okay, and those two things being at war with one another. That's not a biblical idea. Okay? But Euclid is kind of known as the great organizer of the Greek system of thought. Okay? And the way he did it is he started the elements with a bunch of definitions and axioms and common notions, and then eventually postulates. Okay, well, in the postulates, a lot of them were pretty basic concepts that didn't really require proof either. But then once he had kind of laid out the foundation, he started in on the propositions. And then he kind of focused at some point on the idea of parallelism and the like. The stuff that we're talking about right now is basically all going to belong to book 1 of the Elements. Now, there's a lot more than just one book in the Elements, but the things that we're going to be talking about today really kind of reside within book 1. Okay, I am going to show you. So we're going to obviously look at Euclid's proof of the Pythagorean theorem, but we're also going to have a peek at some other proofs that have come down throughout history. I'm not going to ruin it for you. There's pictures there. You can go over to Chuck's and play around with those pictures, and I'm telling you the proofs are residing within those pictures also. There's going to be 3 pictures, one of which came from James Garfield, if you can believe that, former president of the United States. Okay, pretty interesting. Okay, so Euclid is thought of as the father of geometry. Again, mathematical proof, as we know it today, is largely due to kind of his general approach and argumentative style. Plato was a huge influence on Euclid's thinking. And there's an interesting, this is actually in the book itself, in chapter 2, talks about how when you entered Plato's academy, there was this sign over the entryway that said, "Let no man ignorant of geometry enter here." So just kind of this idea that geometry was at the center of what the Greeks were trying to do intellectually. Okay? There was something beautiful about it. It wasn't just arithmetic. Okay? There was arithmetic, and a lot of other cultures had tended to focus almost exclusively on arithmetic. But geometry seemed to pull in this idea of logic and in proof, and there was just more of this abstract realm of ideas that really caused the Greeks to elevate geometry to this place in their culture. Almost all Greek mathematicians following Euclid had some connection with his school in Alexandria. Okay? Nice picture of Euclid there. Probably not accurate, but still a pretty cool picture nonetheless. Okay? So what about the Elements specifically? Well, it was written in Alexandria about 300, right, so this is 300 BC. You guys remember when Hippocrates was doing his thing? Yeah, right, so it's about 5th century, so this is 150 years or so after Hippocrates. The Elements consist of 13 total books on mathematics and geometry. Now, there's a fair amount of number theory in there, okay? In mathematics, and actually in philosophy in general, we talk about things called axioms, okay? And Euclid's approach the sort of the approach itself, the axiomatic approach, is largely due to the elements and the way that you could lay things out. Mathematicians today still do this. Okay? So the axiomatic approach first gets down the things that we won't be arguing about. Sometimes that happens to be like an undefined term. Okay? I mean, if you think about it, I can't define every term that I use because eventually I'm going to run out of words if there's going to be like an infinite regression. Okay? So you have these undefined terms, you have definitions, you have postulates, and 5 common notions. Now, the 5 postulates, I might, instead of calling those postulates, I might recall those axioms, to be honest with you. Okay? Because they're things that he didn't try to prove, and they're just basic items that that he saw as kind of things that were almost self-evident. Okay? So overall, in the 13 books, there's 465 propositions that he proved from this basic axiomatic set. Now, what you do is when you have these axioms, you start building, and eventually, once you prove something, that becomes part of what is known. And that gets drawn into the collection of things that you know to be true. And then you can then use that to prove further things, and then those get drawn in, etc. By the way, the Elements, I mean, this is largely agreed upon. The Elements is one of the most scrutinized books in all of history, okay? Both positively and negatively, honestly. And, Dunham actually remarks that only the Bible has been more scrutinized over time. Okay? And almost all the propositions, even though there were some problems with like things that Euclid was assuming but didn't realize he was assuming them, because just of a lack of general sophistication that only could come with, centuries more time of development of mathematics and notation and whatnot. Nonetheless, almost all the propositions in the Elements are known to be true, okay? Even though we might have thought of some of the proofs or some of the underlying principles to have been missing, all of those propositions have stood the test of time. Almost all of them. So the definitions, okay? His definitions were kind of the basic foundations of what we call Euclidean geometry, named after Euclid. He defined points, lines, straight lines, circles, perpendicularity, what he meant by parallelism, okay? And oftentimes the language that he would use and employ as he went about his business, it wouldn't really be acceptable by modern standards of doing mathematics. And sometimes he was overly verbose. He didn't have a lot of notation at his disposal. So a lot of his arguments are just long, flowing narratives describing every aspect of things, and honestly, sometimes very few pictures to accompany the argument, which is interesting, okay? He tried not to use algebra. He only used it whenever possible. He tended to want to keep things in the intellectual realm and not kind of put pen to paper as far as like doing algebraic manipulations, okay? But the algebra that he did use was only in a geometric context. And what's interesting is he never used degrees for measure. He would always talk about things in terms of right angles, 2 right angles. He would talk about the sums of the angles in a triangle, adding to 2 right angles. By the way, 2 right angles would be 180 degrees. Okay. So interestingly, he mostly described things in terms of known angular entities, like a right angle, for instance, okay? Postulates, again, I would tend to call these axioms, but he called them postulates, okay? These are basically the self-evident truths of Euclid's system, and he only started with 5 of them. Again, I said there were 23 definitions of things that he defined: point, line, etc. But these postulates were like the self-evident truths of his system of geometric thinking. And what were the 5 postulates? Well, some of them you wouldn't argue with at all. But ultimately, most of the postulates are things that you could build using a compass and straight edge. Okay? But there's one that was particularly controversial, and I really want to hone in on that rather than focus on the other four, which most of you would have no issue with at all. The fifth one was the one that's been the subject of a lot of controversy. It's called the parallel postulate. How many of you have ever heard of that before? Okay? Parallel postulate is basically encapsulated in that picture that's sitting right there. And essentially what he said was, suppose I have two lines, and then I have a transversal line, a line that kind of cuts through both of them. And suppose I look at the angles on one side of that transversal interior to those two lines. And the parallel postulate said if those two angles, alpha and beta, sum to less than two right angles, then those two lines will eventually meet on that side of it, on that side. Does that make sense? So if alpha plus beta right there was like 120 degrees, what Euclid was saying is eventually those lines are going to do what? Well, they're going to hit one another. Does that make sense? They're going to intersect on that same side. Now, does that seem like something he ought to assume? You think he ought to assume that that's true? By the way, there's lots of things that are actually equivalent to this, turns out. It's not obvious on its head, but for instance, have you ever heard someone say, you probably heard this in high school, suppose I give you a line and a point not on that line, then there is exactly one line through that point parallel to the beginning line. You ever heard that one before? Line, point not on that line, there's exactly one line through that point parallel to the given line. That's called Playfair's axiom, okay? And it turns out that's equivalent to the parallel postulate, the thing that Euclid just articulated. And there's lots of other things that are equivalent to it. For instance, the angles in a triangle adding up to 180 degrees, or adding up to two right angles. Turns out that's equivalent to the parallel postulate. This is why it caused controversy. Though that seems like a lot to assume. Does that make sense? Assuming at the beginning without proof that the angles in a triangle add up to 180 degrees, that seems like a lot to assume. And so there's been a lot of controversy surrounding that fifth postulate. So everything that is built by Euclid in his Elements assumes these five postulates, the 23 definitions, and we're going to look at some common notions as well. But the one that is the most controversial is this parallel postulate, and that's what this picture encapsulates. Okay? Then common notions. Okay? The common notions are not necessarily specific to geometry. They're really meant to be self-evident. Okay? So like here's an example of common notion number 4. Things which coincide with one another are equal to one another. Okay. I mean, does that seem overly, does that seem like overly controversial in terms of assuming that? No. So the common notions are things that, yeah, we would all just sort of accept, but they're not necessarily mathematical in nature. Okay. So to accept Euclid's propositions, you must be satisfied with the preliminaries. Now, remember, the one sort of thing that's dangling out there and you're kind of like, uh-oh, is that parallel postulate thing, okay? And it turns out that it took a couple thousand years to realize this, but it turns out you could throw out the parallel postulate and actually get a completely consistent geometry without it. In fact, you could assume the opposite of the parallel postulate and still get a completely consistent geometry, but that took about another 2,000 years of thought. What people did for a long time was they tried to get rid of the parallel postulate and prove it from the other things. Does that make sense? So that it was no longer a baseline assumption. But then no one could do it. They were like, why can't we prove this thing? And the answer is because you can get a completely consistent geometry without it. Okay? For instance, doing geometry on the surface of the Earth is not Euclidean geometry. It's curved. Do you know what I'm saying? Euclidean geometry is all flat, planar geometry. Everything is totally flat, okay? But it took a couple thousand years for us to realize that the parallel postulate wasn't something that we needed in order to get a consistent geometry. Okay, let's just talk a little bit about some of his early propositions. Oh, by the way, I want to pause right here. So any questions so far? Questions? Any questions? Okay. Some early propositions. He talked about angles produced by triangles, and in particular proved pretty early on that the sum of the angles in the triangles add up to 180 degrees. He had some clever arguments for why that happened to be true. He actually needed the parallel postulate to prove that, though. And it seems like Euclid himself was slightly uncomfortable with assuming the parallel postulate because he waited like 29 propositions before he actually used it. So he wanted to see how much stuff can I actually prove without the parallel postulate before I can't go any further. And it turns out he proved 28 things. And so the interesting thing is those 28 things that he proved from everything other than the parallel postulate, those things will be true in any system of geometry you happen to look at. Does that make sense? Like whether you assume the parallel postulate or not, because they're independent of the parallel postulate. Okay? Proposition book 1, number 20, says that any two sides of a triangle are together greater than the remaining one. That seems sort of obvious, right? Sometimes in mathematics, we might call that something called the triangle inequality, namely that it's obviously walking from one point to another point along a straight line is going to be shorter than going along the other two legs of the triangles. That sort of makes sense geometrically, right? But it's in this argument particularly that you start to realize that he's maybe assuming things about betweenness and inside and outside. He's starting to get a little bit loose with his language. And it becomes clear that there's probably some things that he should have assumed, at least in terms of definitions and the system he was working in, that he didn't really rigorously articulate. There's been several attempts to patch up the elements later. Sets of axioms numbering close to 20. There were some logicians that did that. Later on, even in the 19th and 20th centuries. And just the rigor, while very good and sophisticated for the time, wasn't quite there. It's in this proposition that starts to become very clear. Again, I want to reiterate, though, that none of his propositions are actually false. It's just he didn't really know he was assuming certain things, it seems. Does that kind of make sense? Okay. Congruence was something he proved pretty early on. Congruence of triangles, and he did this completely through construction with straight edge and compass. He showed that, he showed the side angle side. You guys know that version of congruence, right? Side angle side, okay? So all of these different versions of congruence he actually showed by using constructions with compass and straight edge. Now there's one on here, or there's not one listed on here, where you have two sides and an angle outside of those two sides, SSA. That is not a type of congruence. Okay, I'll let you go to Chuck's and kind of think about that. Think about why it is, if I have two sides and then there's like a third side with some angle outside of those two sides, why it is that you don't get a single triangle. That's a good exercise to think through. Okay? Those versions of congruence actually hold without reference to any kind of triangle sum proposition at all. Okay? They're just true. They don't use the parallel postulate either. That's important, okay, as we've been discussing. You tried to avoid that as long as possible. And he tried to avoid it in future applications whenever possible. But then there are times where he gets literally obsessed with the parallel postulate and just uses it over and over and over again. But I think it's because he couldn't think of another way to prove something. Okay? Let's talk about parallelism a little bit. So parallel lines produce equal alternate angles. That was the first time he used the parallel postulate. Book 1, proposition 29. Angles of a triangle sum to two right angles. Book 1, proposition 32. That also relies on the parallel postulate. Area of a triangle is half the area of a parallelogram with same base and height. Okay? Book 1, proposition 41. how you construct a square on a line segment. Hey, we did that last time. Remember that? We were obsessed with quadrature. The Greeks were obsessed with quadrature for a number of centuries. And construction of a square on a line segment was part and parcel of that. You guys ready for the proof? Let's do it. Okay, so here's the big one, the Pythagorean Theorem. And by the way, Pythagoras is a character in his own right. The book talks about this a little bit. I mean, he almost had a cultish following. Okay? In particular, he had this group of cronies that followed him around. They were interested in it was almost like a commune or something. It was like a mathematical commune, okay? He had this idea that that something was beautiful about things that happen to be expressible as ratios of integers, okay? Because it was connected to constructibility, something that we've been talking about with compass and straight edge. It turns out that if you know something is a ratio of two integers, it will always be constructible. Okay? And Pythagoras discovered pretty early on that there were numbers or distances that were not expressible as a ratio of two integers. But he swore his followers to secrecy. He was like, you cannot talk about this till we sort this out. And at some point, there was an insider that thought, you know what, this is kind of crazy. I think I'm going to go tell people about this. And that person mysteriously disappeared in a shipping accident of some kind, okay? So you have this Pythagorean mob of sorts. He's sort of an interesting character for sure. But one of the things he proved, and actually it was this theorem that gave rise to non-ratio of integer lengths. Specifically, if you look at a triangle that has a length of 1 on one leg, length of 1 on another, you're going to get square root of 2 on the hypotenuse. And he was like, holy smokes, I can't write this as a ratio of two integers. So, and that was a problem in his worldview. Okay? So we all know what the Pythagorean theorem says. Well, let's prove it. And here was Euclid's idea. He basically drew these triangles, or drew a right triangle and drew squares on the sides of that right triangle. Okay, so just so we're clear, the right angle is right there between side of length A and the side of length B. Yeah? So what he wants to do is take these squares and show that the square on the hypotenuse has the same area as what? The sum of the squares on the two legs of those triangles, yes? That's equivalent to the Pythagorean theorem, okay? And it's not surprising that the Greeks would have reduced this to an area problem. Yeah? It's just something that they would have done because they were obsessed with quadrature. In fact, didn't we kind of draw a picture like this when we talked about Hippocrates? When we were talking about combining squares. Remember that? Yeah? And in fact, Hippocrates' quadrature of lune relied on the Pythagorean theorem. And there's a lot of speculation that it was Hippocrates' quadrature of the lune that gave Euclid the idea for this proof. But this proof that we're about to look at pretty clearly comes from Euclid. Okay? Here's the idea. First thing you do is you kind of flip this picture upside down. You have the hypotenuse kind of facing downward. That way it looks like a cool kind of, disproportionate windmill of some kind, okay? And he drops a perpendicular from that point A down to, a perpendicular down to that side down there. Now, that's going to make a right angle down there. And do you see that that's going to kind of automatically split up that big square into two rectangles? Yeah? And here's what Euclid is going to show. He's going to show that that blue rectangle has the same area as the blue square. And he's going to show that, well, it looks red on mine, but it looks pinkish in here. That pink rectangle has the same area as that pink square. Does that make sense? And that would finish the proof, wouldn't it? Because that would show that the pink and blue square add up to give you the big square, yes? If I can establish that that pink rectangle has the same area as that pink square and that blue rectangle has the same area as that blue square, we're done, yeah? So the idea is fairly simple. Any questions on the setup here? Okay. There's something I need to talk about. It's called shearing. And I'm not talking about the shearing of sheep, okay? I'm talking about the shearing of geometric objects. And this was something that the Greeks were also obsessed with. Look, have you ever taken like a stack of papers and you kind of push that, like, you know, a neat stack of paper? I do this on my desk sometimes, just what a nerd I am. You take a stack of paper and you kind of push it this way or that way, like this. Does the height of the paper change when you do that? No. Does the area made up by the edges of that paper, does that change? No. That's still going to remain the same. But you can see that the lengths of those sides are changing, yes, but what is not changing is the base length and the height. Does that make sense? And that idea of kind of pushing the stack of papers back and forth, that's the idea of shearing. And you can do the same thing with triangles. If I can, if I like imagine a bunch of sheets of paper kind of stacked on AB right there all the way up, I can kind of push that stack of paper over, and every single one of those triangles, ACB, ADB, AEB, all of those have the same area, okay? And the way you think of it is you just imagine a bunch of slices of paper in there. You can kind of see that the area is not changing as we shear that around. The base length and the height are the critical things, yes? The base length and the height remain the same, and that's going to determine the area. This is known as Cavaliere's principle, although he wasn't the first one to realize it, okay? It's just, it was named after him much later, okay? What we're going to show is that we're going to draw some triangles in here. You'll see what I mean in just a minute. That together, these triangles are half the area of the large square. And I'll show you what triangles I mean here in just a second. Okay? So does the idea of shearing make sense, hopefully? Okay. All right. When we shear triangles, the area does not change because it has the same base and height. There's also another thing in the picture that Euclid did. You know, it's like at some point you would assume that the right angle would be involved in the argument. Do you know what I'm saying? If we're talking about a right triangle, the right angle would have to be in the argument. And you'll see what I mean here in just a second. But it turns out that there's one critical point where he needs a line to be straight, where he makes use of the fact that we have a 90-degree angle in the triangle itself. And here's the picture. This is kind of the critical picture. And here, I'm going to talk you through it. You ready? We've kind of got this sort of distorted windmill shape. I drop the perpendicular down to the bottom. Do you see that? There's L down there where it hits. I want to show that AGFB, that square, has the same area as KBDL, that rectangle. Does that make sense? And the way I'm going to do it is by showing that half that rectangle has the same area as half that square by drawing some triangles. And there's some triangles I'm going to draw in this picture. And do you see what we've done here? We draw a line from A to D. Do you see it? And there's a little triangle ABD. See the triangle ABD? Here, I'm going to kind of annotate in here a little bit. Okay, it's triangle ABD. All right, so like this guy right here. Okay, and the other triangle we're going to be looking at is this guy right here. Okay. Now, if you just stare at that picture for a minute, what do you think is true about those two triangles? They're actually congruent and hence have the same area. Why are they congruent? Well, first of all, the green triangle has a side FB, correct? You see that? And the red triangle has a side AB, but what's true about FB and AB since they're sides of a square? They're the same. So FB and AB are the same length. Make sense? Okay. All right, let's look at the other leg, BD and BC. Okay, BD is one of the legs of the red triangle, and BC is one of the legs of the green triangle. But those are both sides of the same square, and hence they're the same. So we have two sides so far, and then what Euclid did is he's like, oh, look, the green triangle, the angle between those two sides is made up of a right angle. Look at this. I'm looking at this right here, okay? It's made up of this right angle. Okay, let me use some blue here. It's made up of this right angle and this angle right here. Do you see that? But what do you notice about the red triangle? It's the same angle and this right angle. Do you see that? Therefore, what can you conclude about this angle? Let me kind of use a different color here. About this angle in that triangle and this angle in this other triangle. What's true about that angle? They're equal because they consist of a right angle and an angle that they share. Therefore, these two triangles are congruent by which type of congruence? Side, angle, side. Okay? So those two triangles are congruent by SAS. Okay? But why does that help? Well, it helps because the green triangle is exactly half the area of the square. Why? It's exactly half the area of the upper left pink square. Why? Why is the green triangle exactly half that square? Well, it has base length that's one side of that square, yes? And what's the height of that thing? The height is also the length of the side of the square, yes? You see that triangle has been sheared over like that? And this is where Euclid had to use the fact that this was a right angle. Okay, this is a right angle right here. This is a right angle right here. So this is a right angle so that this right here is a straight line. Does that make sense? So that means we've simply slid that triangle, we've sheared that green triangle over along a straight line, and therefore that triangle has exactly half the area of that upper left pink square. Yeah? Please ask questions about that. Okay, so look, this right here is a straight line that is parallel to this right here, yes? So what is the height of the green triangle? Isn't the height of the green triangle just this? It's the same as that. Does that make sense? Yeah? So look, the area of that triangle is 1/2 base times height, which means it's 1/2 side of the square times the side of the square. So it's exactly half the area of the square. Make sense? By the way, you can do the exact same thing with the red triangle. The red triangle has been sheared in this direction. Yes, it's been sheared along this thing right here. Do you see that it's kind of sheared up in that direction? The height of this guy is this. Does that make sense? That's the height. You see my yellow drawing down here? And the base length is this. Yeah? So what does that tell you about that red triangle? Its area, how does it relate to that rectangle down there? Half. The red triangle is half the area of that pink rectangle. The green triangle is half the area of the pink square. Yes? Therefore, what has to be, but those two triangles are the same area, right? So what does that tell you about the area, the total area of that square and the total area of that rectangle? They're the same. Yeah? It's just a simple shearing argument. Look, if you go over to Chuck's and you kind of think about this picture for a while, I'm telling you, it will make sense. Yes. That's exactly right. So I'll show you a picture here in just a second, and we'll kind of be done here presently. Okay, I'm going to skip this right here. Right, repeat the steps of the triangle that is half the area of the other small square. Okay, here's a total picture of everything that happened. See those two triangles right there, and then he does some other triangles over there. He's going to use the same congruence argument, and he's going to establish exactly what he claimed was going to be true. Okay, it's an amazing picture. By the way, just to kind of finish this off, this picture shows up all over the place in cultures all over the world. And this is the picture that actually comes from, it's from a 1566 edition of the Elements. This is actually the picture of the argument, and then kind of the argument itself given in narrative form as it appears in Journey Through Genius as kind of a little snapshot of the 1566 edition. But I would also look, here's one that, you know, it comes from, it's like an ancient document. It's written in Arabic. Arguments there written in Arabic. And here's several from several different cultures with particular years that these things are dated to. An argument in Latin from 1120, in Arabic, that's from the previous slide, written in 1250. That picture right there, from 800, okay, it's written in Greek. Okay, French, English, Chinese, the same picture shows up all over the place. And actually, if you go to the Smithsonian, like this is a Smithsonian Institute painting that someone did that's kind of a rendering of Euclid's proof of the Pythagorean theorem. It's pretty cool. Yeah. It's kind of been chopped off at the top up there. Sorry about that. But there's the painting. It's pretty cool. And if you read the text, you'll see Euclid actually proves the converse of the Pythagorean theorem. Namely, if the sum of the squares on the legs equals the square on the third leg, then it has to be a right triangle. Goes both ways. Interestingly, his proof actually uses the Pythagorean theorem. Okay? I'll let you go read that. I won't ruin it for you. Lastly, there's been several other proofs. If you go in here into the slides, there's several other proofs that have been handed down through the ages. All of these pictures, if you think about the pictures themselves, you'll get an alternative proof of the Pythagorean theorem. Okay? Well, interestingly, this one that involves kind of a trapezoid shape, see this one down here at the bottom? That comes from James Garfield, the end of the 19th century. Okay? So I won't get into the specifics, but there are other issues I have already mentioned, so-called non-Euclidean geometries coming from either not assuming the parallel postulate or assuming its opposite. There are several different geometries that arose out of that. I'll tell you a story maybe later on about Gauss. He was kind of a jerk sometimes, and he actually, you know, kind of discovered a non-Euclidean geometry and decided not to tell anyone. And then they discovered it later and came to Gauss, and he was like, "Oh, I thought of that like 40 years ago. You fools." Okay? So there's some interesting stuff at the end of the chapter about that. And incidentally, if the geometry where the sum of the angles is less than 180 degrees, there is a consistent geometry where you assume that, you end up getting AAA congruence, which is not something that you have in the Euclidean geometry, for instance. Okay? That's all I have. But you know, I would challenge you to look at those three pictures of the other Pythagorean theorem proofs. Thank you.